So I'll be discussing some basic things, but this will not be in serial. Like I'll just keep on discussing, and then I'll give the introduction there itself, and recent trends, current trends, and the past how we did, like in with respect to the testing. So some basic slides, like we know, electronics are everywhere. Each fields you can see the chips are there, and basically the integrated circuit, without the integrated circuits, no digital or analog or mixed signal operation is possible in current scenario. So we are having lots of developments currently here. So as you can see, first the integrated circuit here, and then it goes to the printed circuit board, and then this printed circuit board goes to the system. So these are some basic things which you already know, and this contains many blocks inside it because it has to perform many operations. So suppose let's take mobile as example, the cell phone. So the cell phone suppose contains this integrated circuit, and this integrated circuit inside it has many blocks. So as you know, you have audio, like you can think of audio chips inside that, then video chips, then some Wi-Fi chips, then some Bluetooth chip, and so many. So basically, inside an integrated circuit, there are many chips, many blocks basically, and then that integrated circuit placed on the printed circuit board, and then this board goes to the system. So now, in like if you compare from last 10 days, like 10 years or so, we see like there are many things in with respect to mobile or computers. We were having monitors, speakers, keyboards, like many things as a separate parts, but now it combined, and we have the laptops. So basically the laptop contains all the things which we have previously, like it has monitor, speakers, keyboards, everything. Like, so what happens is, since the in older days we have separate chips for each of this functionality. So for monitor we have a separate chip, then speaker we have, and that's why we have this block. And now these all chips are combined in a single chip, and we have a tablet or laptop or mobile. So previously we were like in a bigger system, now it is getting compact and compact. So these are some basic things which you already know. So what happens is, you design a chip, then you verify it, you fabricate it, test it, assemble it, and deliver it. So you do for the individual IC, like here you do it for the individual ICs, and then you do it for a single IC by combining all this functionality into one. But this is not the scenario what happens in the industry. Like, this is not the full scenario. I'll be discussing more in depth how it does in the industry. So basically this is the chip, and if you'll open this chip, you will get like this. There is a silicon there, and there is a bonding wires which connects to these pads. So I would like you to just remember these figures, because later it will help to understand. So this is the chip. If you'll open it, you will get a silicon, and there will be pads, and there will be bonding wires which connects the pads. Okay, so how it fabricates? So first, it's fabricated from a silicon, like sand, and basically the TSMC, Taiwan Semiconductor Manufacturing Corporation, or Global Unichip. There are many foundries based on Taiwan and US. Even I think Intel has their own foundry. So basically they use the sand as a basic material, and they use some method to grow that as a crystal, and then the crystal will be very long. Nowadays I think it's 9 inches or more, and then they will slice it, and once they will slice it, they will get these blank wafers. And then there are many steps, as you have already been knowing in the VLSI fabrication step, like creating the N well, P well, then lithography, and then so on. So there are many steps, and then you get the patterned wafer here, and then this wafer are tested, and then you dice it into single dice, and then again you bond it, package it, and then you do the part testing, and then you ship to the customer. So this is the basic idea how it happens, just a general overview how it happens in the manufacturing side. So this is the figure where I would like your attention, like you should pay attention here, because I'll be discussing whole 2 hour with respect to this single slide only, how it happens. So as I said here in this slide, right, this when you open it, it will look like this. So basically I am going to discuss this part, this silicon chip in this slide. So usually in the top level, in the outer boundary, it's called design top, or the top level your IC. And then you have your pad and boundary scan. So pad is nothing but the pins which is coming like at the top, which is mounted, that is called pad. And then you have the boundary scan. So basically pad is of two types, like analog pad and it can be digital pad for digital signal. And then you have boundary scan. I'll tell you the details, like why we are using this boundary scan. And then after this pad and boundary scan, the second hierarchy is pin muxing. So I'll be discussing in detail each and everything why we use this pin muxing, but just an overview. We have the pad first, then boundary scan, then pin muxing, and then we have the compression logic. So we have to compress, since the designs are getting bigger and bigger, billions of transistors are there, so many gates and so many flops are there. So we need to compress it. So we have a compression logic. Now we will discuss more in detail. And then we have some top logic, some security logic, some DFT instrument, some analog block, some hard IPs, some soft IPs. Then we have blocks, as I told, in a chip. You have many blocks like analog blocks, digital block, or if you have, suppose, audio blocks, then you have Wi-Fi block, then you have Bluetooth block, then you have a video block. So there are many blocks, and a block may contain a sub block. So suppose block A contains A.A1, A.A2, and in sub block you have memories. So inside a sub block you can have a memory, or outside a block you can have a memory, or even in the top you can have a memories. So here you can see I am having soft IP and hard IP also. This is the third party IP. So suppose Samsung, let's take example of Samsung or any mobile manufacturing device. I'll take mobile as example because everybody uses mobile. So a mobile manufacturer company may not design all the IP by itself. It may take IP from third party or other vendors. So suppose if a mobile company doesn't design analog IP or video IP, so they will just buy it from the other third party provider. So they will use it in their design. And even in analog and RF blocks, there can be soft IP and hard IP. Because soft IP and hard IP, the difference is here you can basically open the design and you can do some your manual things. But in hard IP, you cannot do it. You should use it as it is, as per their specification. They do not want to open their like IP for the manufacturer, basically, who is going to manufacture this chip. So we have a top, then pad and boundary scan, then pin muxing, then compression logic, and then we have the other logic blocks and this like soft IP and hard IP. So now let's just remember this figure as a overview. So we will discuss in depth, so it will be easy. So now, as I told here in this, you can just design it, verify it, fabricate it, test it, and means it's a very simple, right? Here you can see it's very simple, but it is not simple as it's look. So let's go deep into it, how it actually happens in the industry. So the first step is the customer requirement or the specification. So manufacturer, suppose a mobile manufacturer, they have certain requirements and some specification. So that could be a timeline, a feature in the sense the size of the chip, the number of pins, and the PPA, that is power, performance, and area. Performance in the sense frequency. and of course the cost. So first point here is the customer requirement and specification based on these particular properties. And then it goes to the high level planning. So once the customer comes to you and give their specification, you as a mobile designer, you will do the high level planning. So here the project and product planning happens. So they will do the time scheduling, then they will plan for resourcing because you need resource to design and test. Then you need some software and licenses. Then you also need the storage and database to basically save your designs and files. So this is happen at the second phase. Then once it is done, it goes to the architectural design. So here basically you architect your top level product. So you remember when we open the chip, we get the top level, right? So here that planning happens for that. Basically this planning, this top level and this all blocks planning happens at this phase. So here everything happens like top level, then block level, sub block level. And here it's also decided whether we follow the top down or bottom up. So basically if the chips are big, usually in industry they follow hierarchical designs. So they will just block by block, they will just first finish it and then they will hook that block to the top level or one level higher. And then what are the libraries are required, and then as I told, what are the third party IPs required, either it can be hard or soft. Then you need the models and the micro architecture you do at this level. So here also it decided like which node you are going to work. Like you must be having some 40 nanometer, 16 nanometer, 22 nanometer. Now it is 10 nanometer, 3 nanometer. So all the decision happens here. And once that is done, it goes to the logical and functional design, where you do the Verilog RTL coding, your behavioral coding, and you write the test benches and do the simulation. Currently, they are using system Verilog extensively for this purpose. And apart from that, you check the DRCs or many RTL and other rules you check here. So you use Spyglass, it's a Synopsys tool. Like clock domain crossing, reset domain crossing, I'll be discussing what are those in detail. But here basically you check those DRC design rule checking. You use UPF here. If your chip is like low power, you are doing the low power designing, then you use the unified power format here. It's IEEE standard. And you do the low power checks, which is called VCLP, and it is also supported by Synopsys. Okay, so you understand like after customer requirements how it goes to the logical and functional level. Okay, so once the functional verification and logical DRCs checks here, you use the standard cell libraries, because you have only behavioral model as of now. You don't have any flops, any gates model. So here basically the TSMC or the foundry provides you the cell libraries which has the power, delay and area information in it. And then you use it to verify your logic. And then you do the RTL delivery. So whatever you have designed, you do the delivery. And you do the delivery to the DFT or synthesis team or to the physical design team. So suppose if you are doing delivery here, so there are two methods currently we use in the industry. So either you do delivery to the DFT, I mean this RTL you give to the DFT directly, design for test team, or you give to the synthesis team. So basically in earlier days it was synthesis, means after RTL design we give it to the synthesis, basically from RTL to gate level netlist. So this team generates that. But now in current scenarios, this RTL design we are giving to the DFT team. So basically we are doing all the DFT, we are inserting all the DFT logic at the RTL itself to save the time and other things. Because in synthesis it is difficult. So we'll discuss more in detail in later, but just to understand the flow here. So suppose RTL you have designed and you have delivered it to DFT team. So what DFT will do, they will insert the DFT logic, that is that DFT instrument at the RTL level. So that is nothing but the boundary scan, MBIST and EDT UCC. So this boundary scan is nothing but the BSD, which I discussed in that previous slides, that pad and boundary scan. So this is the boundary scan. And then this embist, this is nothing but if your design has memory in it. So to test memory, there is a technique, memory built-in self-test. So we insert this built-in self-test here. And then this EDT OCC. EDT is nothing but embedded deterministic test. It is nothing but the compression logic which I showed you. And then you have some OCC, on-chip clock controller. So we'll discuss each of them in depth, but just understand the flow, how it works, and then we'll take up each individual in more detail. So you receive the RTL and you given it to the DFT team, and DFT inserted their logic here. And then after inserting, they will also verify using the simulation and all the DRC check. So once the DFT is inserted in your RTL, they will again, this DFT team again verify it. Okay, so please remember we are following this RTL flow here, not the synthesis flow. We will take it later. Then we'll do some quality checks here. So once you inserted your DFT logic in the RTL, you will do the basic synthesis and then low power checks and logic equivalence check, that is LEC. So basically in basic synthesis, we make sure that whatever we have done, it should be at least linked to the library. Otherwise, the synthesis team will get the error and again you have to redo the process. So to avoid that, we do the basic synthesis. And then some low power checks we do to check some of the, if your UPF is there, then all the power crossing boundaries are correct between one block to other block, or inside if there are multiple power domains, so the DRC should be fixed. And then you check the logic equivalence check, like before inserting the DFT logic and after inserting the DFT logic, the functionality should not change. So that's what we do here in the quality checks. And then we deliver it to synthesis team. So synthesis team will take the RTL, that is DFT inserted RTL, and they will generate the gate level netlist. So basically you don't have any flop, cell or model at the RTL level. It's just a behavioral model. Like you might be writing some D flip-flop code. So you'll be using always hat pauses or neg gauge, and then you are doing. So you don't have any physical flop there, any cell there or any model there. So to get that or to map those models, the synthesis team will take your RTL and map it to the gate level. And then they generate the synthesized RTL. So there also they will correct the many DRCs, design rule checks. Then there will be some linking error and some warnings. So they have to correct everything, and then they will generate the gate level netlist. But again, they will do this VCLP and LEC checks, because they will make sure before generating the gate level netlist, that means your like DFT inserted RTL, and after generating this gate level netlist, the functionality should not change. So again, they will check all the power formats, all the LEC, everything they will check. And then they will release the first compile netlist, which is also called ultra netlist. And it will be delivered back to the DFT. So you see some of the DFT logic like boundary scan, embist, and EDTOCC you inserted at the RTL level, and you delivered it to the synthesis. And after synthesis, you get the gate level netlist, the first compile netlist back. And then again, you will perform some more DFT on that. So you will insert a scan onto that, and you do some chain stitching and so many things there. And then parallelly, it will also deliver to the physical design team for their initial flow flush. So now let's go to the next one. So since you receive the gate level netlist here, you will perform the scan insertion and DRC fixes. You will do the DRCs, whatever with respect to the scan, you will fix it here, and you perform the scan insertion. And then you will get the scan inserted netlist. And then again, you have to deliver it to synthesis. Now it is called map. So again, the synthesis team will take your netlist and they will again synthesize it. And here they will do lots of optimization. In the first compile, they will not do so much optimization, but in the second, once your scan is inserted, they will do the power optimization, area optimization, delay optimizations. There are so many optimization in the synthesis step. So once they will get the scan inserted netlist from you, they will again synthesize it, optimize it, and again they will deliver it to DFT and physical design or the timing team, static timing analysis, this timing team. And remember this VCLP and LEC, this will be checked every time your design gets changed. So again, you have changed your design, like you have inserted the scan, then again you have to check, like your functionality should not change and any power related issue should not be there. Then again, they will give the map netlist to the DFT team. So then you will perform the ATPG on the map netlist. You will focus on the test coverage, how much fault you can detect onto your chip, and you will generate the pattern and you will simulate it. And parallelly, since they have delivered to the physical design also for their flow, so they will also start with the partitioning. They will partition your chip. They will do the floor planning, placement, clock tree synthesis, signal routing, and timing closure. So many things they will also do on the same mapped netlist. So the things happen parallelly. And then they will take care of this process voltage temperature, this PVT corners, and they will do the physical verification like DRCs. They will also check the design rule here, layout versus schematic they will check. So, and then some electrical rule checking also they will perform. And they will also perform this VCLP and LEC between the netlist and PNR. After this placement and route netlist, they will perform this parallelly to this DFT. Then, so here the physical design team will generate the PNR netlist. I mean this timing closed and placement and routed, the final netlist they will generate. So whatever you are doing, this is not the final. Final always happens on the PNR netlist, which PD teams gives, because ultimately the PD teams give this GDS file, which will goes for the manufacturing. So we need to do all the things with respect to this PNR netlist. All the things means ATPG. So then you get the PNR netlist, which is timing clean netlist or timing closed netlist, and then you perform the final ATPG on that. So the previous ATPG is just to see your flow is work correctly and there is no issue, but that is not the one which you are going to deliver to the ATE or test team to test on the silicon. So once you receive the PNR netlist here, timing closed netlist, you do the ATPG, and then you generate the pattern and you verify those patterns with SDF, the delay format, the timing simulation, and then you deliver the pattern for the wafer testing or module testing. There are so many testing. So those patterns are actual patterns which are used for the silicon testing. And parallel to that, on the same PNR netlist, the functional team also verifies the functionality, because ultimately that is the netlist which will be taking further for the fabrication of the chip. So on that netlist, everything should be clean with respect to timing. So test team perform the ATPG, and then functional team perform their functionality checks. And then here in the PD teams also, they will do the layout post-processing, fabrication, and then there will be a packaging team which will package it and test it. And if that fails, it goes to the post-silicon debug and then feedback to the silicon team. So you see, right, from the here, we just simply said like it's a design, verify, fabricate, test, assemble, deliver, but this is not the case. So this is the actual case which happens. So there are so many steps. And we discussed only this RTL flow, not the synthesis flow. Some of the company still uses this synthesis flow. That means after designing, they delivered it to synthesis team. So now suppose, till now we were discussing RTL flow, but suppose now we have the synthesis flow in some company. So how it is done is, so RTL team directly gives RTL to the synthesis team. They will not give to the DFT team. So from there, they will directly synthesize it, convert RTL to gate level netlist and deliver netlist to the DFT and PD. And again, they will do this VCLP and LEC checks. And then on next step, the DFT will do all the instrument and all the insertion at gate level. Earlier, this DFT team were doing on the RTL level, but in the synthesis flow, they will do everything on the gate level netlist. Then they will fix the DRCs, clock DRC, reset DRC, there are many DRCs. They will optimize it and they will again deliver this scan inserted netlist to the physical design. And the physical design flow is same as above. So all floor planning, partitioning, placement, this is the same. And then we get the PNR and timing clean netlist from the physical design, and we do the pattern simulation and verification, which we did here in the RTL case. So you see how complex it is. Means it's not complex basically, but it is lots of steps to follow before we tape out or before we give file to the foundry for the fabrication. So I think at least overview is clear now. So this was the overview. So now we will go much into deeper. So now basically, since I am working on DFT, because there are many parts, so there are design parts, I mean design team, like they will code the RTL with respect by using this system Verilog. And then there are verification team which writes this test benches to verify the RTL. Then there are DFT team, then physical design team, then synthesis team, then timing team. There are many teams and many people involved, many resources needed to just design a chip. It's not very easy. So basically I worked on the DFT side. I'm a DFT engineer. So basically my discussion will be related to DFT, and I will starting little bit in depth from here. So basically DFT logic has BST. If you remember the one diagram where we have this pad and boundary scan, muxing and all. So we will go into detail now. So in BST, it's nothing but the IEEE 1149.1 standard. So 1149.1 is nothing but it's for, as I told, we have two pads, analog pads and digital pad. Since we have two different signals, analog signal and digital signal, so we have two type of pad. So this 1149.1, it is for digital pad, and same 1149.6 is for analog pad. So there are difference in testing. So that's why we have different pads. And to handle the signals, there are different ways. And then we have this mixed signal for 0.7 and high speed 0.10. So these are the things we used and mix of them. If we have both, then we have to mix it. The second one is memory built-in cell test. If we have memory, so we need this built-in cell test to test those, because we have different type of fault there. We'll discuss more there. Then we have a logic based. So logic based basically needed for the case where we have suppose if you are designing a chip for a car or for a space, like this rockets and all which goes to the space, so you don't have any physical access, so you should have a built-in self test which can test itself. So there we have this LBIST and all. And then you have this compression. This EDT is nothing but compression. In the Mentor graphics or in Tessent, it is called embedded deterministic test. So it's nothing but the compression. And then we have this OCC, which is clock controllers, and we have also the reset controllers. We'll come to know like why we are using this in detail. And then we have iJTAG, which is very famous nowadays. This is called IEEE 1687. This is the standard. It's called internal JTAG, Joint Test Texan Group. So we'll discuss more on this. You just keep it as an introduction. So we have there a SIB, NIB, we'll discuss. And we have wrappers, that is IEEE 1500 again. And then low pin count test, LPCT, there is a methodology. If you are a pin limited design, you don't have that much pin to test, then use this LPCT, and there are many more. So these are the basic major DFT logic we use to test the chip. And we do wafer chip. As in the previous slide you saw, like if there are a wafer, we do the wafer test, then we slice it, we do the die test, then we package it, we do the package test, then part test, board test, and system test. So there are so many testing happen. And then each of these tests may have the sub-test, like characterization test, leakage test, chip probe test, burn-in test, and many more. Burn-in basically you test in your chip with the extreme conditions, like extreme temperature, high temperature, extreme low temperature, extremely high frequency, extremely low frequency. So that is called burn-in test. So these are the basic introduction of the digital logic, what we do. And there are many more. So we do the functional testing, structural testing, scan-based delay testing, built-in cell test, memory testing, analog circuit testing, system on chip testing, then reliability testing, and basically those things happen on this ATE, automatic test equipment. So once you have the silicon in your hand, you deliver it to the test team, I mean this ATE team, and you also deliver the ATPG pattern which you generated on the PNR netlist. So based on that, they will place your silicon here, and they will apply those patterns, and they will test they will figure out the response, and then there will be a comparator which will compare the your patterns, when you like put your pattern into that ATE, and then it generates some response. So you need to compare that. So you need to compare the simulated response, I mean response from this ATE, and the expected response. So it should match. If it is not matching, that means your silicon, like there are some fault in the silicon or in your setup. So that is called post. Like after that, you do the post silicon debug, like why that failing is happening. Okay. So before going further, let's discuss some of the tools which we use in the industry. So you can see at the top, we have these three major EDA vendors: Mentor, Synopsys, and Cadence. And then we have the tools for DFT, for physical design, timing, synthesis, RTL, layout, and yield. There are so many tools and there are companies. So for DFT, basically Mentor gives the test and cell. So in this, you can perform all the DFT, and then Synopsys do the test max, that is DFT compiler and tetramax, and Cadence has the modus. For physical design, this ICC is used, ICC and ICC2 as a Synopsys. I don't know this name of this Mentor tool and some of the Cadence tool. So what I know, I have placed here. So for physical design, we use this ICC and ICC2, and then Cadence, it's a Innovus. So they are extensively used across the industry. For timing, we have this prime time from Synopsys, and Cadence, we have Tempus. Then synthesis, of course, this design compiler is very famous. And then we have Genus from the Cadence. RTL checks, we have Spyglass from Synopsys. Layout, we have Virtuoso and OrCAD. So basically, OrCAD is for educational purpose. In industry, they don't use this. They use the Virtuoso. So this is from Cadence. And then for yield is nothing but how many good chips you are having out of the total chips. So Yield Explorer and Yield Manager is the tool from Synopsys. We use it to analyze that. So these are some tools which we use extensively across the industry, just for your information. Okay, so now we'll focus more on testing from here onwards. So now let's go to the pad and BST, which we discussed in the previous slide. So just remember the top level block diagram where we had the pad and pin muxing compression, because I'll be discussing around that. So let's take this pad and BST. So as I told, for analog pads, we have this 0.6, 1149.6 standard, and for digital pad, we have 1149.1. And then this JTAG is the group formed by the IEEE, which proposes this. It's very old though, so they propose this IEEE standard to test that. And we have this tab, test access port. It's a FSM with 16 state. And we have some boundary scan cell for the top level BST insertion and testing. So here you can see on a motherboard, let's say 10 different IC are placed, which may be manufactured by different companies. So in a motherboard or in a single board, you say in a chip, you have 10 different components, or in a board 10 different ICs. And you can see here I have written yesterday, means it is a in the past days we are designing like this. We have so less pins and less complexity. But today you can see lots of pins and the complexity has increased, because earlier the transistor count was very less in an IC, but now it's million and billions of transistor. And tomorrow you can get more complex things. So now as the nodes are getting down, 5 nanometer, 3 nanometer, so currently in Apple 14 you will see billions of transistors and so many blocks. So tomorrow you may see this kind of structure. So where in a single chip there are so many IPs or blocks with so complex design. Now earlier, as I told, it was very easy to test also, but today it is very difficult because there are so many blocks involved. Even in Qualcomm, as it uses Snapdragon, it's so complex. So to test these boundaries, because you have to test the boundaries. So to know whether your signal from the outside world goes correctly inside and you can generate the proper response. So to test that, you need a mechanism. So earlier it was easy. Let's go to the next slide. Yeah, so here you can see. So earlier we were using this insert circuit or board of nails where you connect all the signal physically to a nail kind of structure and you test the signals there. But now it's very difficult. You cannot do it. You don't have that access to that. So now you need to develop some mechanism to test that. So that's why this JTAG, this joint test action group formed, and they come up with this standard to test those boundaries. Boundaries means outer logic. Okay. So this is basically the architecture. So basically I'm giving overview here. If I'll go into depth, it will take much more time. In 2 hours I cannot finish it, but I'll just give an overview so that at least you have some clarity like how it does. So we have this 1149.1, let's say, and this is the architecture. So basically we have this tap here, which is a 16-state machine. And we have this TMS, TCK, TRST, TDI, and TDO. These are the 5 important signal. This is mandatory basically, apart from this TRST. So from the chip top, that means from the top level, you have this test data input, test data output, test mode select, test clock, then test reset. Test reset is optional. I will tell you why it is optional. So at least these 4 we need, or these 5. So this signal will go to this tap, the 16-state machine, and this will generate some internal signal like clock IR means instruction register, or DR data register, and then they will generate some shift signal and all. And then based on that, it will select a particular instruction register. And then it will decode that instruction, and then it goes to your system circuitry. So you can see here, basically your chip is placed in the system circuitry, and then you have the boundary registers here. It's just like a wrapper. And then you have the functional input, that is device input, and then your test input. So there is a mechanism to test it. So you have to basically you put your data from this TDI and you shift this data from this boundary scan cells and then shift out to get the response. And you remember we have this bypass register here. So let's see if I have that. No, let's take it later. So suppose in a board, this is a board, you have a 2 chip. So basically you can just put your input from this TDI, shift it through this boundary cells and shift out to the TDO. So basically if you are shifting in and shifting out and you know the expected response, you can always compare it and see if there are any mismatches. And you, of course, for shifting you need the clock, so you need a test clock, and to select any particular mode you need this TMS, test mode select. So basically this JTAG or this boundary scan helps on your top level, as well as internal logic also you can test using that. So basically this is the how it works. So here you have circuits prior to the boundary scan, then you have a boundary scan cell, and this is your IO pads, as I told, analog or digital pad. You have the pad, and then boundary scan, and then you have your circuits, and then you have this tap mechanism or IJTAG mechanism to get this circuit tested. Now that this tap, we have the 16 state, right? So you can see here, this is the tap architecture or tap FSM, where we have the 16 different architecture. So basically this TDI, TDO, TMS, TCK are the mandatory, TRST is your optional. So based like using this FSM, we generate all the internal signal like shift, capture, update, everything we generate using this. So as I told, TRST is optional here. This is because this TMS, right? This TMS signal in your chip, you can put TMS signal 5 times, like for 5 clock cycle high, and it will reset your logic. So like in any case, in any stage, if you are there, like suppose if I'm at the exit 1 IR, like I'm exiting this instruction register, DR is the data register. So if I'm at any of these state, and if I put TMS high for 5 clock cycle, I'll reset my tap. So that's why this is optional. So if I'm exit, you put TMS as 1 here, so TMS goes to the update, then TMS you put update at 1, so it goes to this select DR, then put TMS as 1, again one, it will reset it, test logic reset. So in any of the state, you can put TNS 5 cycle high and it will reset it. That's why it's optional. So if you have the pin, you can use it. Otherwise you don't have, so you can just use that mechanism. So this is my tap, this tap controller, which generates all the internal signal to basically decode it or to test the circuitry. Yeah, so this one I was talking. So in the test data registers, we have some mandatory and some optional registers. There are many more, but these are the basic. So these are the boundary scan registers, which I told, like around the pad we have a boundary. So those are the mandatory. Then we have a bypass register. Bypass register is nothing but, suppose in a board you have 10 different ICs as we discussed, and you want to bypass first 2 ICs and test the only third IC, or you bypass first 5 ICs and you want to test the 6th IC. So there it is used. So to bypass the first 2 ICs, you can just use the instruction and you bypass that IC. If there is a muxing logic there, it will bypass the first 2 and it will go to the third, or basically to bypass any of that, this is used. So that's why it's a mandatory. And then you have the instruction register. So basically you need the instruction to perform any of the operation, so that's why it's a mandatory. Then you have this device ID, like you have 10 different IC from 10 different manufacturers. You want to identify which of that device, like which device it is. So you can have this device ID register, and which is optional, it's not that much required. And then design specific register. So whatever the specific, like ASIC you are designing, so based on that you have some design specific register there, which is also optional. And there are many more. These are just 5 for example, but there are many more. So as I told, this I already discussed, like instructions are fed serially through TDI into the instruction register, and then circuit is configured based on that instruction, and then test instruction is executed and then shifted out through TDO. And once you are shifting out, you can immediately shift in the next data through TDI. So this is a basic fundamental operation. And the boundary scan cell, as I told, you have the logic, you have a tap, and then the boundary scan, just a wrap around. So this is your boundary scan, and basically it looks like this. So this is just a one example of boundary scan. I think it's a BC cell 1, boundary scan cell 1. And there are 7 different BC cell, and because you have input, you have output, and some of the pad maybe have like in-out. So for each individual pad, you need a different kind of cell. So you need like BC1, BC2, BC3 till BC7, we have 7 different boundary scan cells. So this is the basic structure, how it does. There is a capture register, there is a update register, and there is a 2 muxes. Basically this is a mux. In IEEE they use this symbol for the mux, where this mode, through mode is the select line, and you select between 2 different signal, and here the shift DR. So this mode, shift out, capture, shift, and these are all tap generates the signal, but this parallel in, parallel out, it's your device signal. I mean, it's your device functional signal from the top. So basically just a basic operation. So we have 4 basic operation, like normal, scan, capture, and update. So for the normal mode, so this mode, right, if mode is 0, you can your parallel out will be paralleling. So you can directly pass this parallel input to the parallel output by using this mode 0. So the first one is the normal mode, like functional mode. Then you want to do the scan. So in scan mode, you put shift DR is equals to 1. So basically you use the first mux. So put shift DR is equals to 1. So it will select the shifting. Shifting means that from TDI, the data you are shifting. So you will shift it from here, and then based on the clock DR, it will latch it here in the shift out. So that's what it works in the scan part. And in capture, it's the same. You just use this clock DR signal, and you capture this shift DR shifting data here, and you put it to the shift out. And then in the case of update, you put mode is equals to 1, and update DR mode is equals to 1, this one, so that I will select this path and update DR, and it will latch your data to the output. This is just a fundamental basic operation of any boundary scan cell. So this is how we use for normal scan, capture, and update. So basically this is one cell, but we have this 4 or 5, depends on the how many instruction you have. Like suppose you have 5-bit instruction or 4-bit instruction. I mean to say, suppose you have a let's say 10 instruction to perform on a chip. So to perform 10 instruction, you need four like four different cell, because in binary system you need like 0000, right? Means from 000 it's a 0 to 7. So you need 4 different bits to perform 10 different instructions. So for that you need 4 different BC cells. So that's why it depends like how many instruction you have. Suppose you have 17 instruction, then your bit become 5-bit, because it supports only 0 to 16, right? 0 to 15, I mean 16 till 16 you can count using 0000 or 1111. But if it is 17-bit, then you have to increase your this instruction size, and your this BC cell will increase. So based on the number of instruction, basically decided, and this is the basic operation. Then there are some important test modes. So it has around, I think, 10 different test modes, but basic is that these 3 we use extensively: this X test, bypass, and in test. So bypass I already told. Suppose in a chip you have these 3 blocks and you want to test only the middle one, or you want to test the third one, so you have to bypass it. This BP, this bypass register, you have to use, put the instruction of the bypass, and it will bypass these 2, it will test the third. Or you want to test only the second, so you bypass first and third, you test the second. And then X test means the connectivity check between these 2 chips. So some of the signal will go from one chip to other chip, and this connectivity between these 2 chips will be tested by X test. So basically you shift in the data from here, and then you shift out, and again shift in, shift out. So basically you test the connectivity between these 2 chips. And there is a in test, which will test the internal logic. This internal logic, it will perform the test. So these are the 3 basic or important test modes for the JTAG. And there are many other modes, clamp, high G, there are so many, but just to make it easy, we focus on these 3. Okay, so till now we have seen the pin muxing. Till now we have seen the BST. So if you'll remember this diagram, this one. So I would suggest always remember this one. So we discussed till now this pad and boundary scan. Now we'll go to the pin muxing, then compression, and then some of the internal logic. So we have just, and it just overview. We have just overview how this boundary scan works. Now we are coming to the pin muxing. So one hierarchy down to the BST. So as we know, like we have limited number of pins. There is no not availability of the multiple pins used for the test, because there are some analog pin, digital pin. Then we have the limited design, like limited pins. Then we have to use the pin muxing, like we have to use the mux logic to get it like propagated towards our block, which is placed inside. So there are huge number of multiplexers we use. Okay, so I have put just a simple example here. Suppose you have a mux where the select line is test mode, and you have a functional clock, we have a test clock, and then output of this goes to the many other logic. So basically the difference between test clock and functional clock, your test clock will always be slower, because the ATE, that automatic test equipment where the silicon will be tested, will not support the high speed clock, but your chip will work on the high speed, so functional clock. So to shift the data, you always use the test clock. So you need this is just example, you need a mux. Basically you make the test mode as 0, so it will take for functional clock. You made 1, it will take the test clock. So you don't have different pads for that, so you will just use the muxing logic. So this is just an example. You have many such signals. There are various signals which we use this mux to propagate it to the next logic. So this is what the pin muxing. It just pin muxing, nothing but a huge number of multiplexers which will select based on your signal and based on your which mode you are. Now the third hierarchy is the compression logic, as I told. So we have seen the BST, we have seen the pin muxing, now we see the compression logic. So in compression, basically what happens is you have a decompressor and you have a compactor. Basically these two basic element we have in the compression logic. So suppose you have a millions of gates, billions of gates, you have so many flops, flip-flops in your design, and you can just imagine as a shift registers. You have so many shift register, you want to create a chain by using those shift register. So since there are many flops, like suppose 50,000 flops, so you want to make a chain, so it will be, and you have only suppose 40 pins, so the chain length will be higher, right? So suppose you have a 40,000 flop and you have a 40 pins, and that you cannot use all the pins because there will be analog pin and digital pins, so you are supposed to use only the digital pins. So the chain length will be high if you don't use the compression logic. So to avoid that, we use this compression logic. So basically we have a decompressor and compactor. So inside the decompressor, we have this ring generator, or it's a LFSM kind of a structure here. And then we have a phase shifter. So phase shifter is nothing but it's a XOR gates. So inside this block, there are trees of XOR gates. So basically you have only suppose these 2 or 3 or limited input for this decompressor, and then you give this input to this ring generator. It will take that 2 or 3 whatever the input, and it will generate many number of output. So there are a mathematical equation here, like how many input it takes and how many output it generates. There are a equation, but suppose it takes 2 input and generates 20 outputs. So you see you reduce the number of channel required or pin required from the top. So in only 2 chain, like 2 channel or 2 pin, you generated the 20 different, you taken control of these 20 different chains. And we use phase shifter, like if you XOR this all 20, then you can generate many more here. So suppose you want to compress further, you can just XOR many signal and generate the different output from this phase shifter. And then you can concatenate your scan chains here. So this will be shorter chain now, because if suppose I was not using this decompressor, our chain length will be higher, but now our chain length will be smaller because we are giving 20 different inputs from here. Now in the output side, in the compactor side, basically we compress it. So again here we have this XOR gates here. There are lots of XOR gate. We XOR many outputs from here and then we put it to the compactor. So basically we are compressing here. And then after compressing, we will compare here. We have in the AT, we have this comparator, which will compare the expected and simulated response. So to make it easier, like the chain length and patterns and all, we use this compression logic. So let's discuss little more, like inside how it works. So this is just overview. Maybe make a full screen. So let's go to this. So basically you like in the earlier there are no clocks, no other signal, but here you will see you need the EDT channels. So as I told, this is a bus, so you need channels at least 1, 2, or depends on your architecture how much channels is allowed. And there are EDT clock, EDT update and scan enable. So based on those signal, it will generate all the internal signals. And then suppose you have this decompressor or compressor as a faulty, means your decompressor and compressor itself has a fault. Then for that, we also use this bypass logic, bypass module. So to test this decompressor and compactor basically. So you can just bypass this core and you can test it. So if there are any defects in the compressor and decompactor, you can easily detect it. So here we are not showing any functional pin. These are just test pins it's required. So here you see the mask shift register. So between the last slide and this slide, you see only this mask shift register and there is a EDT mask signal. So this is basically what happens is, suppose you want to mask any chain. There is a problem in any chain. You created a 40 chains and suppose some of the chains are output, like on their output you are observing X, because it's coming from some analog blocks, some memory blocks which are not controlled, and it is throwing X. So you have those excess here, so you need to mask that, because in AT you don't have, you have only 1 and 0, you don't have X and high Z. So you have to mask that. So for that you use this mask registers. So there is a logic inside, we'll see later. So basically you generate that masking concept like logic here, and it will mask that particular chain here. Yeah, so as I told, in the decompressor side, you have the channels, then LFSM, which will check 2 input and generate 20 or many outputs. And then you have a phase shifter, which is nothing but the XOR gates, and then it connected to the internal chains. So basically this latch is required. You can see here we are using this lockup latch. So basically it is required to avoid the data loss. So suppose you have 2 flops, right? Flop 1 and flop 2. And flop 1 is working on pause edge, like rising edge of the clock, and pause, like flop 2 is working on the neg edge, like falling edge of the flop. So if you draw the waveform, there will be a data loss between that. So to avoid that, we use that lockup latch. The tool uses like inserted this based on that analysis. Then we have this decompressor module with mask shift register. So we have this masking logic here. So suppose any of the channels, as I told, you want to mask it, you generate this logic from here and you put that logic to your internal chain. Yeah, so then the third one is the bypass. You bypass your internal chains. So basically there is a problem in the decompressor or compactor side, or there is a problem in your chain itself. So what you do, you just take output from each of the chains. So you have 8 chains here. So you take output of that chain and again concatenate it with the second chain. So basically you are generating a long chain by using this short chain output. So you can see here the bypass output is combining all these 8 or at least 4. So you have mux multiplexer here, which will, one of the input will be this 4 and the other input will be 5 to 8. So you are just making longer chains to debug it. Then you have the compactor module, as I told. So from core chains, the output will goes to this masking logic. If there are any excess in your chain, it will mask any of the chain. And then you have again this lockup latches and then this XOR gates. And then you have pipelining to make it faster. And then you have the EDT channel out, where your output from these chains will come. And this is your bypass, output bypass logic, how it bypass, which we saw here. This bypass mechanism in more specifically shown here. So basically you concatenate all the internal chains and you make a logic here, longer chains, and it will bypass it. Bypass in the sense it will concatenate 4 of the chains and make a single chain. Then you have a single chain bypass. So suppose you want to bypass a single chain or 2 or 3 chains, depends on your design or depends on the error you are getting. So again you use the multiplexer on that particular chain output and just bypass it. So that tool will not generate that chain, it will just skip that and it will generate pattern for the other chains. And this is your masking logic. So as I told, in the masking logic, you have a logic here, you have a mask shift register, you have a mask hold register, and then you have a decoder. So basically masking logic is nothing but an AND gate. So AND gate, suppose one of the input is coming from the chains and second input, this decoder will make as a 0. So since it is an AND gate and one input is 0, so output will always be 0. So basically you are masking it, you are not allowing this gate to propagate the signal from this. So here you will get a 0 and based on that it will proceed to the other logic. So there is a very complex logic inside. So we generate that masking here and then based on that the particular decoder will be selected and then particular AND gate will be get activated. Otherwise this will be 1. So the chain we are masking, that logic will be 0. So this is the same thing but in a more specific way. So you have a mux. So based on the EDT update and EDT clock, it will hold that particular value and it will, based on that it will select. And based on the XOR decoder or one hot decoder, you select a particular signal on that and then it will goes to that output. So as I told, the and in the AND gate, one input will come from the chains and the other will come from this mask register, and that will generate a 0 for the particular chain based on the your like what are the requirements, which channel you want to mask. That particular channel pattern will be saved here, and this decoder will select that particular chains here, so that you are not masking unnecessary the other chains. Then we have a dual compression configuration logic. So suppose this is the advanced thing. So suppose current, like in the last slide we were seeing the single compression, but in a same thing we can do the dual compression. Like your half of the internal chains will be compressed in a separate way and the other half will be compressed at the separate way. So this is the C1 C2 kind of structure. So if you are not understanding much on this, it's okay, because it's a kind of higher level architecture, so which we use in the industry. So just for overview, you can just look at it. So again, this is the same. If you have a dual compression logic C1 C2, so we use different type of compactor here. And then we have a power controller. So this we will take up. So basically what happens is you have the internal chains and you want to control the power, like you have a patterns to be applied from the EDT channel in. So you want to reduce the power. So basically what we do while shifting, we reduce the toggling, because if your signal is toggled more, it will take more power. Your core will take more power. So we'll control that toggling here. And for that we use this low power shift enable. So suppose if you are designing your chip for the low power application, so you use this low power shift enable. So basically what it does, your shifting will be done based on the less toggling. So if you toggle it less, your power will be less. So there are some other logic here we use, and it will be implemented at the input of the output of the decompressor, but input to your core internal chains. So based on that signal, your toggling will be less, and hence your power will be reduced. So till now we were discussed compression here. So we discussed pad and boundary scan, we discussed the pin muxing, we discussed the compression logic, and now we are discussing internal instrument, DFT instrument, like internal to that block or internal to that particular logic. So the first instrument is IJTAG, which is nothing but internal JTAG or IEEE 1687 standard. So earlier days it was very difficult to send a signal from top to a particular block or to sub block. So now basically currently in all the industry they are following this logic. So suppose this is block 1 and block 2 and you want to test it. So this standard makes it very easy to access all the signal from here. So if your block is IEEE 1687 compliant, so it has the ECL and PDL in it. So ECL and PDL is nothing but instrument connectivity language and procedural description language. So it has the information of the block, and it has some mechanism to directly access from this tab. So we see this test access port, right? TDI, TDO, TCO. So using this tab, you can easily access those instruments, and using that instrument, you can easily test your block. So IJTAG make it very easy to test any of your block using those instruments. So currently we are using this IJTAG for the block level testing, and we have to just port it. So suppose block 1 you did the testing, and you have to just port it to the top level, because ultimately you have to run this block from the top level. You don't have any direct access to this block, so you need to access those using this TDI, TDO. So using this IJTAG, it's very easy to access that and test that. So this is one of your TFC instrument which we use. So this is the more detailed diagram. So you have this tab signals here, you have a tab, it will generate this, and this SIBs you have segment insertion bits. So you can think like a mux or so. So out of the many block, it will select a particular block, like you have this IPs, intellectual property blocks here, and based on that it will select the test data register. So you can see this TDR is placed in front of the block, and you can just through TDI you can shift in the data and shift out and using the sieve you can again make it as the TDO. Through TDO you can measure it. So using this 1687 or IJTAG, it's very easy to test any of the block. You have a very easy control or very easy access to any of the block using these TDRs and SIPs. Now, this is to test a particular block or to test a particular instrument into it. Now we have the MBIST. Suppose any of your design contains the memory. So to test memory, we use this built-in self-test. So basically what happens is, suppose this is your RAM, SRAM or DRAM, whatever, like you have a memory here. So memory generally contains the address, data, control and data out. So we insert a logic, so which generates your test address, test data and test control. So you can see from here BIST controller. So basically in a block you have a memory. To test the memory you insert a controller. So basically this BIST controller generates the test data, test address and the control signal. And you have muxes here. Muxes because this memory has to be tested with respect to the testing frequency and with respect to the functional frequency. I mean, functional team also test it with respect to their requirement and test team also test it. So to bifurcate it, we need this muxes here. So during test mode 1, it will take the data from this controller and it will test it. Again, you have the comparator here. So you take the data out and you have the response stored here, like your golden response. You compare it and based on that you will tell like your memory is passing or failing. And if it is failing, again you need to open the waveform and debug it, like why it is failing. And there are various fault involved in this memory. So suppose some of your like address decoder, it's stuck to 0 or it's connected to VDD or VSS. So that address you cannot test. Or suppose in a coupling, there are coupling faults. So based on one address, your another address gets some fault, or there is a short or open between that. So you cannot test it. So based on this mechanism, you can easily test that. So this is another DFT instrument called MBIST, or another logic which we call MBIST to test the memory. Then you have this top, you have a sub chip, you have a sub block. And as I told, like memories can be at the top level, at the block level or at the sub block level. So you need the controller to generate the signal, like test signal, test address, test data and so on. But the thing is, suppose you must be thinking why we cannot test the memory using one controller, right? Why we use multiple controllers? This is because we have a different types of memory. So single port, dual port, multi-port memory, and these memories may not work at the similar frequency. So suppose these two memory works on same frequency, then two works on the different frequency. So the controller has a limitation. It cannot generate different frequency clock or control signals. So we group the memories. So suppose these two memories working at the same frequency, you group them and we use one controller for this. This is working on the different frequency and this is different type of memory. We use different controller. So based on that, we need to insert the controllers, and based on that controller will generate the test data. But suppose some of the memory gets faulty, like you later figure out like some of the memory is having fault. So how to repair that fault? So in the industry, we use this built-in self-repair. So basically we have some spare inside the memory, we have some spare redundant row and column, which we don't use for the normal functional use. So we just keep it as it is, so that if we discover any fault later on, so we can use those spare cells and we can like instead of that faulty address, we can use that spare cell address and we can easily correct that. So to store those responses or that information, we use the eFuses. So at the top level, you have a eFuse where you store all those informations like redundant row and column information and their address and all, and you generate that logic from there if there are any faults. So this is how it like memory BIST happens. So it's not required like BSR in every chip, but self-repair is there. Many of the industry uses these self-repair techniques. Now the another thing is logic BIST. So logic BIST is similar to the build like memory BIST. It has a circuit under test. It has the logic BIST controller. It will generate the control signal for the test. You have a random number pattern generator here, and you have a signature register. So basically, you will come like comparator will be here. You can compare it. So this controller will generate the control signal for this circuit under test, and then you have your patterns, ATPG pattern, and then based on that control signal and patterns, it will test internal logic and it will compare with the stored logic. So if comparison is like matching, so it will pass, it will signal as a pass. If it is not matching, it is a failed. Then again you need to dump the waveform and see why it is failing. So basically this is the top level design, and then you have this LBIST. Basically nowadays LBIST is like LBIST we are taking along with the EDT. So we are using this both logic together. So we have the LBIST and EDT here in these two blocks. We have this BIST controller here. So basically from tap itself, we are generating this control logic and we are testing the particular block. And there will be again muxes to test. Suppose if you don't want to test block 2, you want to test only block 1. So you can bypass it, or you can use the muxes here to select the particular logic here. So this is another DFT instrument. The next DFT instrument is on-chip clock controller. So as you saw, we saw the BST, then pin muxing, then compression logic, then IJTAG, MBIST, LBIST. Now this is OCC on-chip clock controllers. So actually, basically why we need on-chip clock controller is your chip pad does not support high frequency clocks. So if you want to test your chip with a high frequency, it cannot be tested because the pad doesn't support it. There is a limitation. So to generate the fast clock, we need these clock controllers. So you can see this logic inserted to SoC for controlling the clock during silicon testing on AT, because AT doesn't support fast clock. So we need some logic where we get the fast clock, because during capture of the faults, we need at the functional frequency, because ultimately when your chip will work, it will work on the functional frequency, not on the test frequency. I mean, it will work on the functional clock, like high speed clock, not on the slow clock. So fast clock doesn't supported by this AT. So, but we need to test on the functional clock. So for that, we need this on-chip clock controller. And for at speed testing, we require at least 2 pulses, one for the launch and one for the capture. And that 2 pulses, this on-chip clock controllers will generate. So this I already explained, IOS doesn't support, and OCC uses the internal PLLs. So there will be phase lock loop inside in your block, which will generate the clock, and the OCC use that PLL to generate those fast clock. So just we have a complex circuitry for OCC, but just for the basic understanding, we have this circuit. So basically you have a flop here where you put the shift enable, and you have the scan clock. So in class, this is scan clock is nothing but your slow clock. So you give this to this, and it will also goes to this mux. And then you have a functional clock as well here. So this will come from the PLL. So the thing is, you need some of the flop. As I told, you need 2 different pulses during the capture. So you need some mechanism to generate those pulses. So once your at speed mode is 1, this mode will be selected, and then your functional clock will come, and based on that scan enable, this will generate the output. So suppose your test mode is 1 here. If it is 0, if test mode is 0, so that means this functional clock will be bypassed. That means you are in the functional mode, you are not in the test mode. That means you're shifting your data. But once your test mode is 1, you are in the test mode, like you are in the shifting mode. So 1, then it will check for this scan enable. If your scan enable is 1, that means your scan clock will be bypassed here. That means you are shifting your data, like you are just loading your data to the flops. But suppose this scan enable goes low, that means you are in the functional path now. So this functional path, then this logic will come into picture, and then this at speed mode will be 1 here, and then based 1 or 0, based on the number of pulses you need, based on that, this OCC output clock will generate it. So in the waveform, you will easily see how many clocks and how many datas are there. So this is another kind of instrument you can say. So this is clock controller. Similar to that, we have a reset controller. So on-chip clock controller and on-chip wrapper controller. I think this is the last. There are many more, but I think this is the last, this wrapper logic. So currently what we are discussing, like by considering the top level module, this one, we were discussing by considering this chip. But now suppose you want to test a block. So similar to this boundary scan and everything compression, we use the same thing, similar logic here at the block level. So suppose if you are doing bottom-up approach, means we are testing block by block, and then here I just for simplicity I represented 2 blocks. There are many blocks, 20 blocks. It depends on the complexity. So suppose you want to test the particular block, right? So to test that block, we have this logic that is called 1500 or wrapper logic. This one. So this is your core in the sense either your block or sub block. Basically it's a block. So in the block you have some functional input, functional output, right? You have some test input and test output. So IEEE 1500, that is called the wrapper logic, is developed to test the core, to test the block. The similar way, like 1149.1 or IJTAG or BSD developed for the top level. Similar way, this wrapper logic developed for the block level. So you can see similar kind of wrapper instruction register, wrapper bypass register. You can see wrapper cells, wrapper ports. All the things are like similar to your boundary scan level. So basically to isolate, suppose you have a 10 different cores, you have a top chip, and you have a 10 different sub block into that chip. So we test using this wrapper logic those chip. So suppose you want to test 2 core, suppose you want to skip first 2 core and test the 3rd core. So you can use this again, this bypass logic to bypass those cores and test only the 3rd core. So the mechanism is same as for the top level logic, but just a little bit logic difference here. So you have you have a TDO, right? TDI, test data input. You have a wrapper serial input here. So you just put the serial input here, and this will be connected again back to the top level TDI. Then you have a bypass register, then again wrapper boundary register. As you have this IEEE boundary scan register, you have a wrapper boundary register, and then you have a functional input, and then functional output, and there are some serial output register as well. So basically the architecture is almost similar to that boundary scan, but little bit different because it's a block level, so you need more signal and all. So this is to test the particular core. And now I think this is the last one. So suppose if you have a pin limited design, and currently everywhere we see the limitation of pin, we don't have that many pin to test. So suppose you have only 40 pins or limited pin for testing. So we use a concept called low pin count test. This is also from Mentor, I think. So from top, suppose you have many less pin, and you want to generate many signal. So there is a concept of this LPCT, and then this is the type 3 LPCT where we use clock and this input channel, and there is output channel. So we have only 3 pin here, but there are many type 1, type 2. There are many LPCT. I think 2 more, type 1 and type 2, and this is the type 3. So we use, depends on our requirement, we use the type of the LPCT. So currently I have taken this type 3 because we are implementing type 3, and this is the one which uses the less number of pin. So the basic idea is, you can see this EDT update, EDT clock, scan enable, EDT bypass, EDT low power, right? So suppose usually this signal has to come from the boundary, but you don't have that many pins. So to solve that issue, we use this logic. So basically you just have a clock port, you have a channel port, and you have a channel output port. So basically you put those signal here, and there is some internal logic which will generate all these signals internally. So you don't need these signals from the top. So it will generate for your decompressor, for your compactor, and then your LPCT clock generator, and then you can easily test your particular block using this logic. So this is very handy logic for the pin limited design. So there are drawbacks, like there are what you call, there are like some advantage and some disadvantage by using every logic. So here basically the complexity will increase, there will be more logic, and there will, I think it will be little bit slower, but that's okay. Depends on the for which application you are designing your chip, or which application you are designing your block. Based on that, you have to decide whether which type of LPCT is needed. Okay, so now if you'll see, let's go back to this diagram, like this slide, this one. So you see, now we have discussed this PST. I have not discussed this 0.7, 0.7, 0.6, 0.7, 0.10 because it's a similar, just a little bit change in architecture. Then we discussed MBIST, LBIST, EDTOCC, then IJTAG, wrapper, LPCT. There are many more. There are some internal to that particular companies, they have their own methods. So there are many more logics, but these are the basic major logic which every industry uses. So we discussed overview of everything. We have not gone in depth because in 2 hour lecture it's not possible. It takes a lot of time to complete. So I have just given the overview how it happens. So we have given the overview, and then I have taken the example, this one, as a chip top, and then there is a blocks and how they are tested. So let me tell you one more thing here. So to test analog blocks or RF block, we have a different method. We cannot test it using those instruments. So the analog DFT, analog design for test, is something else. So these analog blocks are tested in a different way. So that is a different separate part altogether. And then soft IP and hard IP is nothing but, if the third party is giving you the hard IP, so they will give you only the patterns. They will not give you much detailed design information. So you can just use those patterns and verify it. You cannot open it and see it. But in the soft IP, some of the IP you can open it and you can manually change many things inside it. So many companies, like many IP provider gives hard IP, many give soft IP, depends on like NDA, whatever the disclosure agreement you are having with them. So we were here. So now we have covered almost all the instruments in the overview level, and then basically we'll try to see the scan logic. So basically this is suppose a block. So before scan it looked like this. So you have some combo logic, you have some flop, again some combo logic, some input outputs. But once you insert the scan, like once you get this from synthesis and you insert the scan, then it looks like this. There are some other signal will be there, scan in, clock, scan enable. So basically there will be a mux which will differentiate between the functional path and the test path. So suppose if you inserted the scan, so it will look like this. And suppose you have made a chain, so the black, this is a flops which are represented in the black. So you just make a chain using those flop and then scan in and scan out in the shift mode, right? Yeah, so basically flops are nothing but it's a logic gate, basically, AND gate, OR gate. So if you open that, and ultimately these gates are nothing but the transistor. You have that NMOS, PMOS transistor and their connectivity. So basically this AND gate, suppose this A input is stuck at 1. You can see here stuck at 1, stuck at SA is stuck at 1, stuck at 0. So suppose this in a chip, this gate is stuck to VDD. It goes and this wire is connected to VDD and this B. So if it is connected to VDD, that means this signal will always be at 1. It will not be at 0. So that means fault here, if it is stuck at 1, so you cannot detect it is stuck at 1 here, because this will always be a 0. Always it will be as a 1. So to detect 1, you need to force it to 0. And if you force it to 0, you need to propagate it, then B can be anything. So C will be 0. But since it is stuck at 1, it will always be at 1. So you cannot force it to the 0. So this fault cannot be detected if it is stuck at 1. Similar way, if it is connected to ground, so this will be 0. So you cannot detect it 1 here, 0 here, because you need to force opposite value. So whatever the node you want to test, so if you want to test it is stuck at 1, you need to force it to 0 to see the behavior at the output. And if it is 0, you need to force it to the 1. But if it is connected to VDD and ground, you cannot change it. So that those things basically we are testing just to test that this so much architecture we need. Okay. So now basically, I think this is the last slide. Yeah. So basically we have a different fault types. So we just see stuck, if your any node is stuck to VDD or is stuck to ground in a chip, there are many other faults. Like a node, it is slow to rise and so slow to fall. Suppose this A is connected to clock. So that clock is slow to rise and slow to fall. That means that rising edge and falling edge is very slow. So that is come under at speed testing, or we call it as a transition testing. So your transition is very slow. So there are many types. So like stuck at fault, then transition fault, then IDDQ fault, then cell delay fault. There are many fault which we use to detect. So like suppose in a block, suppose some part of the like transistor are slow, some are fast, because you use different models. It's not like any uniform model you use for all the design. And then this pattern generation in simulation, we already discussed, like we generate the pattern to detect those faults, and then we simulate it to see if we are able to detect all the faults or not. Even though everything is passes, but once the silicon is manufactured, you get some defect. It's called manufacturing defect. So you do the post silicon debug and provide feedback to the test team, like this is the fault we have found out and we need to again redo it. And that's how it goes on, the testing goes on. And recently you might be hearing this 3D ICs and this streaming scan network. So basically 3D ICs are nothing but you are stacking one into the other. So basically one IC, then you are stacking the other IC, then you are stacking the other IC. So DFT also is challenging here because the complexity is increasing. So like we are exploring different ways to test here. And there are streaming scan networks. These are also currently industries are exploring into this. So basically how we can test a chip by using just a single in and single out. So suppose if I have a single input and we have some internal logic as LPCT we saw, which generates all the internal logic, and through single output we can just shift out and see the like behavior, whether the comparison is correct or not. So this is how it happens. So I think I have few more minutes. I will tell you a few other things here in this one. Yeah. So here what I supposed to say is, suppose block A and block B, and you just assume there are 10 blocks. So block 1 to block 10. So it is not necessary like all the blocks contains the memory, all the blocks contain instrument. It is not necessary. It depends on design requirement. This is the first point. The other point is this block may be having a slow transistor. Maybe some requirement is like that, like this is the not that important. It has the slow transistor. And suppose block B has the fast transistors. So there will be, and also apart from the slow and fast transistor, there will be a power domain also. There will be different power domains. So suppose block A is working on higher power domain, it requires higher power. Like this block B requires low power. Then, and if some signal is going from block A to block B or block B to block A, there are some communication happening. So since both are working at a different power domains, you need to isolate it. So we place isolation cell. If you will not place it, it will throw excess. So any X is the bad for any design. The other part is, suppose this block A is having higher priority compared to block B. So in a mobile, if you are doing something and if any call is coming, you see everything is interrupted and the call will be given the higher priority. So there are many methods which we use to design a higher priority block than to lower priority block. So it depends on your application, what you want. So in a mobile phone, call is always a higher priority than to play games or anything. So if anything you are doing, And if call is coming, everything will be interrupted. So that part of the logic will be on higher priority. Okay. The other part is there will be some sleep transistors. So suppose if you are like this display, right? You see sometime your display goes off, and once you click the button, it will go down. So there is actually a sleep transistor working inside. So there is a time limit. If you put 10 second, 15 second in your settings, that sleep transistor will be activated and your mobile phone will go into the sleep mode. And also you can see there are a background apps will be running inside your chip. So suppose if you are doing anything, reading any PDFs or playing game, and if you have not exited that, if you are not clear it will be there in the background, it will be running it. So that will also like impact your power thing. It will be there, it will take little bit of power and it will be retain its value. So basically what I'm trying to say is, in your design, in your RTL design or in your digital design, you have different types of flops. So it's called single bit flop, multiple bit flop, then a flop with save and restore feature. So basically there are different, if you'll go more deeper into that, you'll see those architecture in detail. So basically it stores it, and if you want it, it will retain it. But if you'll clear your cache and if you'll restart it, it will take some time. So I just wanted to think into a little bit deeper, like how basically it works. So if you have mobile, you can just think of it, how basically it works. So you'll get to know like where and all this sleep transistors and this like adiabatic logic and all plays into the picture. So I think that like I have given the overview. It's not much very detailed because in 2 hours I cannot give much more detail into that. So this is a basic fundamental like presentation how we do. So I tried to cover a basic overview picture how a chip is tested from the top to the block. So it completes the full overviews. Like if you open this chip, you will get a silicon and how basically it is designed and tested. So I think I am done. If you have any question, you can ask me. Or if you want to know anything a little bit more, you can ask me. I'll try to answer it. But this is the overall general picture, how we do. So the past, as I told, in the past, we are having the less complex circuit. So we have different method to test. But now the complexity has increased. So we have a boundary scan, we have a IJ tag, we have a MEMBIST, and the future is like 3D ICs and then SSNs. Like you have a limited pin, then how to test. So this is like this presentation will be useful for the VLSI or electronic engineers who wants to go into the VLSI industry. So there are many branches, like someone wants to be designer, someone wants to be tester, someone want to be physical designing. So these are all the different. Don't think like one people will do all the things. There are many teams and many person involved in each and everything. So it depends on your interest where you want to go. Like you want to design something, you want to test it, you want to physically design it, you want to lay out your design, or which one makes you more interesting, you can just choose it. And for research perspective, always this remember this PPA, power, performance and area. So how you can reduce the more power, how you can optimize your design with respect to power. So you can see this UPF manual, you can get more idea, or any low power design methodology, how we are doing, like we are using clock gating cells and so on and so forth, data synthesizer, clock synthesizers and all. So for research perspective, this power is the one area which we are focusing, because we are using lots of transistor in a very small space. So the leakage power and all, it's coming into picture. So power is the thing. Then area, how to reduce the area, and then performance, like frequency wise. So if you'll see the power formula, right, it's a P is equals to half CLV square F. So basically you have to play around those, how to optimize the design with respect to power, with respect to area, with respect to frequency. That is what the industry is doing. And then different technology. So I will also tell in the research perspective, this routing, you have the signal routing here. So basically the signal routing currently it's happening through the physical wires, but there are some research going on to transmit the signal using the optics. Like through using the optics, you can transmit the signal, so you don't need the physical wire there. So there are some research going on that field. Then research going on this 3D IC, then SSN. There are research going on. Then this timing side also there are research going on, and then of course this power is always low power designing is always a research topic. So I think I have given a clear overview, like where and all you can focus, and this flow and all you can just go through later, and you can see where is the interest. Or you can use the Google to see how more in detail, like how it does, and you can decide your like field of work. So my domain is testing, so I have given the overview of testing. But similar to that, there is overview of Verilog designing, like digital designing, then similar thing like physical design, then layout. Those are all separate things and separate topics to be understood and to be looked at. So I think thank you. I think I have covered most of that. So thank you for listening, and I hope at least 10-20% you are like you have got the fundamental to think much on it and to work on it. Yeah, thank you.